the last bit on the binomial theorem as such is just looking at the idea of the relationships between the different coefficients and proving some different results. Everything starts with the binomial theorem. So the first step in all these questions is to simply go, okay, what's the binomial theorem? So we can write it in sum notation, like so. So just using the general term there saves a bit of time than writing all the terms out. Mind you, if you're trying to find a pattern, sometimes it is easier to write the expression out. Usually not a bad idea to chuck the general term in the middle there somewhere. And let's have a look. So the question has asked us, what is the value, the sum from k equals 1 to n of nck? So basically, we start with the binomial theorem. There it is. 1 plus x to the power of n is equal to that sum. And we just compare the two and say, well, how can I make the binomial theorem look like that? Via a substitution or some mathematical operation or so on. So if we have a look at the sum, we won't worry about the numbers at this stage. We're looking for nck. We have nck x to the power of k. How can I turn nck x to the power of k into nck? And usually the easiest way is going to be via a substitution. In this case, a logical substitution would simply be x equals 1. Because 1 to the power of anything is going to be 1. So if we let x equal 1, we'll get 1 plus 1 to the power of n is equal to the sum of nck 1 to the power of k. Well, 1 to the power of k is 1. So we almost have it. But of course, our binomial theorem goes from 0 to n. They want from 1 to n. So I need to subtract the term where k equals 0. So 2 to the power of n would equal nc0 plus the sum of k equals 1 to n. So I've pulled out that term where k equals 0 out of the sum. I'll move it to the other side. nc0, of course, is always equal to 1. And there we go, we get our relationship. It does bring up another interesting relationship there. This line here, 2 to the power of n is equal to the sum of k equals 0 to n of nck. It's basically saying any row in Pascal's triangle, so all the binomial coefficients will always add up to be 2 to the power of n. That can sometimes be a handy thing to remember as well. nc1 plus nc3 plus nc5 plus nc7 and so on. Well, there it is in sum notation. For this one, it's probably easier to write the whole thing out so I can compare. What is the difference between the two? Well, we have no x's, of course, so that's easy to sort out. We can make x equal 1, but if I make x equal 1, I've got a problem. Because I'll end up with nc0 plus nc1 plus nc2 plus nc3. That's not what they've asked though. They just want the odd ones. So I need to get rid of all the even ones. So what I do is now let x equal -1, and the signs will alternate. And I can create some simultaneous equations. So depending on whether I want the odd or the evens, I can add or subtract. We want the odd ones, so I'm going to subtract for this one, won't I? So if I subtract, I'll get 2 to the power of n is equal to, now be careful here, that's not saying 2 to the power of nc1, it's 2 times nc1 plus 2 times nc3. So I've got twice all the odd ones, therefore if I just divide both sides by 2, so the left hand side will become 2 to the power of n minus 1, we'll get our relationship. So all the odd ones add up to be 2 to the power of n minus 1. What would all the even ones add up to? Sorry? Same thing. Right? Because we know all of them add up to 2 to the power of n. So if the odd ones add up to 2 to the power of n minus 1, then the even ones must be the difference between the two, which would also be 2 to the power of n minus 1. Okay. KNCK. So what's different here? Well, again, we got the x issue, but we know how to sort the x issue out. That's not a problem. But I need to get k in front of nck. So we have to think about it. Well, here's my general term. What mathematical operation will get that k to the front of the term? Well, differentiation will do that. So if I differentiate both sides, so the left-hand side, n outside of 1 plus x to the n minus 1, the right-hand side will become k times nck, x to the k minus 1. Now if we do a substitution of x equals 1, that gets rid of the x's on the right-hand side. We're almost there, aren't we? But we want from 1 to n, so we'll pull out the k equals 0 term. Mind you, that's just 0 anyway when we have a look at the actual term. And we get the sum of k equals 1 to n of k. nck is n times 2 to the power of n minus 1. Okay. Alright, so there's our binomial theorem. Well, this time, what's different? Well, it looks like we're not going to substitute k equals 1 in. If you look at it, we've got minus 1 to the power of k in what we're trying to prove. So logically, we're going to end up substituting in x equals negative 1. So that'll come later. But I need to create a fraction, and the denominator is k plus 1. So we need a mathematical operation that'll do that for us. In this case, that'll be integration, because we'd add 1 to the power over the power. So if I integrate both sides, but here's where we've got to be careful, because when we integrate, we'll get a constant. Yes, we'll get a constant on both sides, but bring it all to one side, because we're going to have to work out what that, I've called it capital K for constant. All right, so what have we got? We know we're going to end up substituting x equals negative 1. Well, let's work out that constant. If I let x equals 0, that's probably going to be the easiest way to work out the constant, because my sum will end up being 0. So I'll end up with 0 to the power. Well, it's always, every single term is going to be 0. So that gets rid of the sum on the right-hand side. My constant turns out then to be negative 1 on n plus 1. All right, now I'll let x equal negative 1. How close are we? K equals 0 to n, yes. nck minus 1 to k plus, ooh, close. They want minus 1 to the k. I've got minus 1 to the k plus 1. So I just have to divide both sides by negative 1. That'll fix that up. So if I divide by negative 1, then it becomes negative 1 to the power of k, but the right-hand side now, instead of being negative 1 on n plus 1, becomes positive 1 on n plus 1. This type of question is where we use an identity and we say, hey, I can express this binomial expansion in 2 different ways. And by doing that, I can look at the coefficients on one side and compare it to the coefficients on the other side, and they must be equal because it's the same expression. So this one here, we've got 1 plus x to the power of n times 1 plus x to the power of n. That would be the same as 1 plus x to the power of 2n. And we're going to use that to show that the sum from 0 to n of nck all squared is 2n factorial over n factorial squared. All right, well, there's our binomial theorem. This time I will write all the terms out just to make it a little bit easier. Now, remember, on the left-hand side, we're multiplying that expression by itself. I want to pull out all the coefficients of x to the power of n. So the nc0 in the first parentheses would have to be multiplied by the x to the power of n term in the second parentheses. And, whoop, there we go, that one times that one. So we'll get nc0 times ncn x to the n. Then the nc1x would have to be multiplied by the ncn minus 1 to the power of x to the power of n minus 1. So we get nc1x, ncn minus 1, x to the n minus 1. And we can keep matching up like that. And eventually we get the last term where the ncn x to the n would be multiplied by the nc0 in the first one. Now we're just interested in the coefficients, so I'll get rid of all the x to the n's there. We have nc0 n times ncn, and so on and so on and so on. Well, the other thing we know about the binomial coefficients, or Pascal's triangle, is the symmetry. So NC0 and NCN are in fact the same thing, and NC1 and NCN minus 1 are the same thing. So I could rewrite that to be NC0 squared plus NC1 squared, which in some notation, and that's the left-hand side of what we're trying to prove. So the right-hand side, let's have a look. We're now looking at the coefficient of x to the power of n in 1 plus x to the power of 2n. So that expansion would go 2nc0 plus 2nc1x, and so on and so on and so on. Somewhere in the middle, there would be a term that says 2ncn x to the n. And it's the only term in the whole expansion that is x to the power of n. So that is the only coefficient on the right-hand side. Well, these coefficients must be equal. Not quite what they've asked us to prove though, because the right-hand side, you remember, was in factorial notation. So let's now use our definition. We'll get 2n factorial on n factorial, and of course n factorial could be written as on n factorial squared. So from our book, we've got those from 5F. I also put in there some worksheets, which aren't too bad to work through. It gets you through the idea of the binomial coefficients and what have you. I guess the trickiest bit is the setting out, because sometimes it feels like you haven't done anything, but just explain what you're doing clearly as you go along, so they can see that, especially when they show that. You show that they're telling you what the answer is. So you don't want to be accused of, oh, you just wrote the answer down. Or you show where it came from.